Right. So remember that we've talked about we've talked about la somme entre deux espaces vectoriels. Now this is some generalization. This is the generalization. Instead of taking the sum between deux espaces, deux sous-espaces vectoriels, we take the sum between p sous-espaces vectoriels, such that the first item here comes from the first item, then the second item here comes from the second item, from the second espace, and then the last item comes from, excuse me, now the last item comes from the last espace. So it's the same thing, but we've just generalized. So we've taken the sum over n sets instead of taking the sum over p. Instead of taking the sum over over two spaces, we've taken it over p spaces. Okay, so that is la somme de sous-espaces, right? So let me just locate where we are. Now let's define what it means for two spaces to be ensemble direct. Ensemble direct. Now there's one thing that I want you guys to understand about this sum. This new set that we've written. There's one thing that you guys are supposed to understand, is that we know that if I take a vector x that is in f1 plus f2 like so, then this x is going to be written in the form, x1 plus x2, where x1 is going to come from the first set, where x1 is going to come from the first set, and x2 is going to come from the second set, or from the second espace, sous-espace. Now, there's the representation of x here. The representation of x is not unique in general. This representation of x is not unique. This is what we are saying here with this example. So here they've taken a simple example. They've taken f1 as this espace where we have alpha, and beta, where alpha and beta are any two real numbers. So we also have f2 for the second one, where we have gamma, delta, delta, where gamma and delta are any two real numbers. So an example of a vector that is going to be in f1 is the vector 1, 1, 1. And then an example of a vector that is going to be here is 2, 2, 2. So all you just have to do is that the numbers that you plug in here are supposed to be real numbers. So you can't put something like I here, for example. You have a problem here. But you just have to respect the condition that the vectors are supposed to have real valued components. That's what this means. But alpha and beta, and gamma and delta can be any real numbers. So this is what we have here. So here they are saying it's easy to verify that f1 and f2 are subspaces of E. Now what is E? E is equal to R3. Now let me remind you that R3 is the set of vectors that have three components. So there's a component here, then there's a component here, and then there's a component here. So they have three components, right? Okay, so let's verify that f1 is a subspace of R3. So let's first of all verify that f1 is non-empty. So we know that the zero vector of R3 is this vector here that has 3 zeros, 0, 0, 0 like so. So this is the zero vector for R3. Now, is this zero vector in f1? Yes, it is. All you have to do here is to take alpha is equal to beta is equal to 0. Then f1 is going to be equal to 0. Now, is the zero vector for R3 in f2? Yes, it is. All you have to do is to take gamma is equal to delta is equal to 0. Then the f1 and f2 are going to be non-empty. Then do we have stability by summation? Of course, you can easily verify. Do we have stability by scalar multiplication? Of course, you can easily verify. Now, f1 and f2 are subspaces of what? Of R3. We now define a new set, f1 plus f2. Okay, we define a new set f1 plus f2. Now let's look at how this vector can be written as a vector of f1 and as a vector of f2. So this same vector 1, 2, 1 can be written as 1, 1, 0 and 0, 0, 1. Now this is clearly a vector of f1 because alpha and beta and gamma here are real numbers, and then 1 and 1 and 0 are real numbers. So this is clearly a vector of f1, and then this is clearly a vector of f2. So this has been written as this. Same thing. This same vector can be written as this vector and this vector, where this is an element of f1 and this is an element of f2. So here we see that the takeaway here is that, here is the same thing. It's the same thing here. but we see the same thing. This same vector 1, 1, 2, 1 is still written as this and this. So where this is still an element of F1, and then this is an element of F2. So we see that with the set that we've defined, there's nothing unique about the x's representation. There's nothing unique about this x. Okay, this x, the representation of x in as a sum of two items, where the first item is coming from F1 and the second item is coming from F2. This is not unique in general. So this is just something that you're supposed to remember. Then it makes sense now that we define this new notation, where we're talking about la somme directe, where we have this notation that instead of putting a plus, we're putting a plus with a circle. Okay, so soit E en K espace et F et G, des sous-espaces de E, la somme de F et G et le sous-espace de E noté par. So with this, we've already talked about la somme. And then en particulier, la somme de F et G est dite directe. So instead of only having la somme, we have la somme directe. So we're going to say that the sum is going to be direct if the representation of x as an element of as a sum of an element of f and an element of g is unique, then the sum is going to be direct. So previously, what is our problem here? The problem we have here is that with the sum, with only this definition, the representation of x as the sum of an element of the first sous-espace and the second sous-espace is not unique. But if the representation is unique, then we're going to say that la somme est directe. So this is what they've written here. We're going to say that la somme est directe. Now, this is about if the vectors. So if I say soit, the sum is going to be direct. So here we're going to say the sum f plus g is going to be direct. If I take an element, it's going to be direct if soit x, an element of f plus g, where f and g are two subspaces, then we can find a unique xg. We can find a unique xg, and then we can also find a unique and seul xf, such that x is equal to xf plus xg. If this is going to mean that the sum is going to be direct if this x, that is an element of f plus g, can be written in a unique way as the sum of two items of the first set and the second set, or the first espace vectoriel, sous-espace vectoriel, and the second sous-espace vectoriel. Now, we're going to say that f and g are going to be supplémentaires. If every vector of the parent space can be written in a unique way. Now, for the first definition, for la somme directe, the x is coming from f plus g. And then for supplémentaire, for the part where we have supplémentaire, the x is coming from E. If every vector of E can be written in a unique way, x is equal to xg plus xf, then this sum is going to be, then the two vector spaces f and g are going to be supplémentaires. Pay particular attention here. Please, look, what do we have here? We have f plus g is going to be direct if vectors of this sum can be written in a unique way. X is equal to xf plus xg, where xg is an element of the second sous-espace and xf is an element of the first sous-espace. But if we're talking about the elements of this vector, elements of the parent space, which is E, if they are written in a unique way, if we now take the vectors from E, we also find that they are written in a unique way, xg plus xf, then the two subspaces f and g are going to be supplémentaires. So hopefully you get that. So that is about la somme directe and the difference between just having the sum and la somme directe, and then also the condition of supplémentaire. Okay, that is what we have. And then how do you calculate the dimension of the sum? So you can use this theorem, the dimension of the set. So let's say now here it's the same thing. I've just replaced f1 and f2 with f and g. So if we have two subspaces f and g, if we have two subspaces f and g, the dimension of this new set, the sum, la somme de deux espaces, is going to be equal to the dimension of f plus the dimension of g minus the dimension of f intersection g. Now this looks similar to something like this. The cardinality of two sets A union B is equal to the cardinality of A plus the cardinality of the set B minus the cardinality of the intersection. So this looks similar to this. We won't prove this theorem. Now if you're confused that why have I used f and g, let me just go back to what we used. Let me just go back to what we used so that we don't have any confusions. Any confusion. So soit f1, f2, deux sous-espaces vectoriels de E, we have the dimension of la somme de ces deux sous-espaces f1 plus f2 is going to be equal to the dimension of f1 plus the dimension of f2, and then minus the dimension of f1 minus the dimension of f1 minus the dimension of f1 intersection f2, like so. So you see that is the same thing. I just replaced f and g with, f1 and f2 with f and g. Okay, this is what I've done. So if you look at, let's go back to the previous slide. So for la somme directe, if you want to show that deux sous-espaces are going to be on somme directe, all you have to do is to show that every element you take from this sum f plus g, or this sum f1 plus f2, every element you take is going to be written in a unique way. But that is going to be very tedious, and it's not always possible to show that every element can be written uniquely in the way xf plus xg. So there's a better way to show that two subspaces are going to be on somme direct, or there's a simpler way to show that two spaces are going to be on somme direct. There's a simpler way. Instead of showing that every element of the sum f plus g can be written in a unique way, x is equal to xf plus xg, there's a better way. The only thing that you have to do in this particular case is to show that the intersection is the zero vector. That only the zero vector is in the intersection. We cannot find any other vector apart from the zero vector in the intersection. So that is the necessary and sufficient condition. So let me just look for that part. Let me just look for, I think I didn't include it here. So let me maybe write it here. Oh, I have it here at the end. So here, this is what I say. This is the better way. This is a better way to show that two spaces f and g are on somme direct. Now, the first thing that you want to do, so to show that f1 and f2, now f1 and f2 are subspaces of E. So to show that f1 and f2, to show that f1 and f2, to show that f1 and f2 are on somme direct, that is, to show that f1 is on somme direct with f2. So the goal, you have to show that f1 intersection f2 is equal to the zero vector of E. So meaning the only vector that is in the intersection is the zero vector. That is what you're supposed to show. That is simpler than showing that every vector in the sum f plus g can be written in a unique way. Okay? As the sum of two elements, where the first item is coming from the first sous-espace vectoriel, and the second item is coming from the second sous-espace vectoriel. This is a much better and easier way. It's not always possible to show that some vector can be written in a unique way. Okay? So hopefully you get it. So the necessary and sufficient condition for two subspaces to be on somme direct is that the intersection of the subspaces has to be reduced to the zero vector. Let me write it. Let me just write that here so that you remember. So the necessary and sufficient condition, the necessary and sufficient condition for two subspaces to be ensemble direct, the necessary and sufficient condition for two subspaces to be ensemble direct is that the intersection their intersection should only contain the zero vector, like so. So let me just put that here. So this is the necessary and sufficient condition. So if you want to show that deux sous-espaces sont ensemble direct, all you have to do is to show that their intersection contains the zero vector. We'll see with the exercises that are going to follow how we'll be able to apply that particular principle. But then let's look at this formula that we've seen here. This formula that we've seen here. What is it going to become if f and g are ensemble direct? What would be the dimension? Oh, here we see that C, F, and G ensemble direct. So if F and G are going to be ensemble direct, then the formula is going to be, then the dimension of F plus G is actually going to be equal to the dimension of F plus the dimension of G, because the dimension of F intersection G is equal to 0, because F intersection G only contains the zero vector. So the formula simplifies to what we have here. So this formula, le formule de Grassmann, simplifies to this if the two spaces are ensemble direct, because the intersection is reduced to the zero vector, and so the dimension is going to be 0. So the dimension of F plus G is going to be equal to the dimension of F plus the dimension of G. C'est très simple. So this is what we have here. So we'll look at these exercises that are going to follow. Next time we'll be able to solve these exercises. So this is what I wanted to show you guys, and hopefully next time we'll just be solving exercises. Okay, I'll see you guys next time.